Hello everyone, I hope you are doing well. So in today's video, we are going to go through the 2022 Northern Hemisphere Physics Exam Short Answer Questions Part 2, where we'll be pretty much, I think, continuing off from question 11 to question 20. And so like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 11. An experiment is set up at a linear accelerator research facility to study muons. The muons created at the research facility are measured to have a speed of this, alright? One muon has a lifetime of this as measured in the muon's frame of reference. Calculate the muon's lifetime as measured by the researchers shown working out. What a beautiful, easy questions. So basically, I'll just draw a basic diagram to see. Now, we know what muons are. Basically, what muons are is, say this is the surface of the Earth, and we have a muon particle basically falling towards the Earth at that speed. Now, what do we know? We know in the frame of reference of the muon, it's going to see length contraction. So L, length contraction. And for a person that's on the Earth, a scientist in the case, he's going to see time dilation. So if he's seeing length contraction, he must be also measuring proper time. This person here must be measuring proper length. And that's it. So we already got our places. We know what, which frame of reference measures what. So one muon has a lifetime of 2.3 microseconds as measured in the muon's frame of reference. So in its frame of reference, it's measuring time, which is our proper time. Remember, in the muon's frame of reference, it's going to measure proper time. So, all right. And we want to calculate the muon's lifetime as measured by the researchers, which they will calculate the time that's dilated. So let's write everything down. So proper time is what? 2.3 microseconds. Now, we don't want to change, microseconds to seconds just because the answer is going to be itself microseconds. So just going to be more work. So just leave it the same. And so we know that we want to calculate proper time. Time that's dilated, which is proper time times your gamma. Theta is, so it's basically 2.3 times 3.2. And that's going to give me, basically, 2.3 times 3.2. Oops, I made a mistake. 2 times 3.2 gives me, to two significant figures, 7.4 microseconds. So let's write that down. 7.4. In one observation, a 0.950 C muon travels at 1.5 kilometers as measured by the researchers. So we're measuring length from this researcher's point of view or frame of reference. So the researchers are going to be measuring proper length, basically. That's our proper length. If measured in the muon's frame of reference, would the length be the same, shorter, or longer? So remember, in the muon's frame of reference, what is it going to be measuring? It's going to measure length contraction. So in basically the muon's frame of reference, it's going to see the length. It's going to be basically contracted. So it's going to be basically shorter. So length is going to be basically, if measured by there, would this be shorter? I think you just, when it says length, I'm just going to write, do I put the length here? I mean, this is confusing. Wait, if measured in the muon's frame of reference, would this length be the same, shorter, or, longer? Use calculation to justify your answer. Okay, so, of course, it's going to be shorter, and I think we just have to calculate what it's going to be. So, shorter. Beautiful. So let's calculate. So basically we have a different speed. So we're going to have a different, Lorentz factor. So remember Lorentz factor, right there. So Lorentz factor is 1 over the square root of 1 minus the speed of light. So what speed was it going? So 0.950 times 3.0 times 10 to the power of 8. All squared, all being divided by the speed of light. So 3.0 times 10 to the power of 8, all squared. And that's it. That's going to give me a Lorentz factor of, alright, okay, that 0.950 times 3.0 times 10 to the power of 8, being all squared, 3.0 times 10 to the power of 8, being all squared. Beautiful. So that's going to give me basically 3.2 2. And so to calculate, of course, what we're trying to calculate is, remember, this is our proper length because it was measured by the researchers. Yes, so we want to measure in the Moore's frame of reference, which is going to be, length contracted. So length contraction is proper length over your Lorentz factor. So it's basically 1.5 all being divided by 3.2. Now, I don't think, it's not saying in meters, so I don't have to change kilometers to meters. So I'm just going to leave it as kilometers, basically. 1.5 divided by that. So I basically get, to two decimal places, we'll say 0.47. So kilometers. That is it. That's going to be contracted length. That looks great. Any mistakes? Look, it looks nice. Beautiful. Let's have a look at this. A transverse wave travels to the right along a length of a string at a speed of this. Figure 8 shows the wave at one instant in time. Calculate the frequency of the wave shown in figure 8. Alright. So, we're given the speed, and so we want to calculate the frequency. We know that frequency, so velocity is frequency times your wavelength. So if I want to calculate frequency, it's going to be my velocity over wavelength. Now, what is my wavelength? It's given here, actually. Remember that what is the wavelength? What's the definition of wavelength? A definition of wavelength pretty much is how long, in meters in this case, how long is one cycle, basically. How long? So the length of one cycle. So for example here, the length of one cycle, well, each of these units here is 0.1. Well, so for one cycle, starting from here, that is one cycle of a graph right there. So overall from here to here, that's one cycle. And so that's going to give us our wavelength, which is basically how much? 1, 2, 3, and 4. 4 times that. So basically our wavelength is 4 times your 0.10, which is basically, just want to check, 0.4 meters. Done. And so we just sub it all in here. So what was the velocity? 8 meters per second. So 8 all divided by 0.4. And that's going to give me 20 hertz. Done. Next question. On figure 8, draw the wave as it would appear 25 milliseconds after the instant shown. Show any calculations and state any assumptions that you have made. Alright, let's have a look at this. So, if they've given me the time, I really want to try to calculate the period, because I think that would very much help me in seeing how the shape would look. So, if I can calculate the period, so the period would be what? So we know that period is the time that it takes for one cycle, like the length of one cycle. So the period is what? So it's 1 over the frequency, which is 1 over 20, the one that we just calculated, which is 1 over 20. Basically, it's 0.05 seconds, but we want it in milliseconds, so we want to times it by 1,000 to get it in milliseconds. Basically, that gives me 50 milliseconds. What does that tell me? It tells me that one cycle, basically, let's have a try. I'm going to try to draw in a bigger color, so let's say in a red using a bigger font. So basically it tells me that if I want to, one cycle starting from the origin like this, it would take 50 milliseconds going from here to go one cycle to the other cycle, one cycle to the other cycle, like that. So basically it will take 50 milliseconds to go from here, this part of it, to go to here, basically. But have a look at this. What it shows here is that's 50 milliseconds, but it's saying draw the wave as it will appear 25 milliseconds, so halfway. So if this basically takes 50 milliseconds to go from here to here, but half of it, so halfway, so while it was going, it would stop over here, 25 milliseconds. So the graph would look like this, basically. So just from looking at it, it basically looks like, and if I want to draw it, it basically looks like this. So it would look like this, basically. like that. So I'm going to basically just draw it nicer by just basically copying the photo here. Like that. And I'm basically going to, okay, so that, and just basically shift it like that. Nice. And what I'm going to do is basically duplicate it. There we go. I'm just going to rub this little part out. There we go. Beautiful. That looks great. Alright, so it says 2 marks. So basically draw it, I think it's 1 mark. The other mark, basically, so showing you calculations. I mean, I just needed the time, the period, and state any assumptions. Yeah, I mean, that's basically it. Assuming that the speed hasn't changed, yeah. Next question. C. The wave source not shown in figure A is now adjusted to increase frequency. Ooh. Explain the effect that this will have on the wavelength, stating any assumptions that you have made. Now, you should know, if you increase frequency, your wavelength decreases. And we can actually just prove it by your, velocity. Oops, that's a too big of a font. So we know that because velocity is frequency times your wavelength. Assuming, because it says stating any assumption, assuming that the speed stays constant, which is basically was 8. Assuming that the speed stays constant. And so what would this have on the wavelength? So wavelength is therefore 8 over frequency. If we increase this frequency, remember, because frequency is in the denominator, if you increase it, it's going to decrease our wavelength. And that's what's going to happen, basically. Beautiful. Yeah. So I think to get the marks, you basically just say, the first mark basically comes from the wavelength decreases. And what assumption? The velocity is constant. And yeah. And you do want to show the kind of formula that you used. So let's write a nice statement. This is a nice question right here. So I want to try purple. Yeah, that looks good. So the wavelength decreases as from V equals F lambda, assuming that the velocity is constant. The velocity is constant, which is basically 8 meters per second. Done. All right, that looks great. Next question. Question 13. Students are investigating the interference of waves using a source of coherent microwaves, 2 narrow slits and a microwave detector. Figure 9 shows the microwave traveling from the slits to the detector. Beautiful. Question 8. The frequency of the microwave is 12 gigahertz. Calculate the wavelength of the microwaves. Okay, so we want to calculate the wavelength and we're given the frequency. Straight away, this is easy. Remember velocity. Same formula. So you remember that velocity is equal to frequency times wavelength. Now remember, it's a laser or a microwave source. Basically, the light is going at the speed of light. So we want to calculate the wavelength. So wavelength is velocity over frequency. And so the velocity is the speed of light. And your frequency is 12 giga. So giga is times 10 to the power of 9 if you look at in your, basically your formula sheet. And so that's going to give me 12 times 10 to the power of 9. That gives me 0.025 meters. So that's my wavelength, basically. All right. B, using the information in figure 9 and your answer in part A, calculate the path difference between the 2 waves arriving at this detector. Give your reasoning. So we want the wavelength. All right. So we want the path difference, The path difference. So remember, the path difference is just basically the distance between the slits and the path. So this distance, also the distance of this, and it's just the change in between them. So what's the distance between this slit and the detector, and what's the distance between this and the detector, and you basically minus them. Now, guess what we have? We have something that's going to help us. Because we have the wavelength, and remember what we said, the wavelength tells us the distance a full wave, basically an actual full wave, a complete wave like this, it tells us the distance of it. So having a look over here, what I can see is that, let's first have a look at this, the length of this from here to here. Now, what I can basically see is that the time it takes to go, the length from here to here, which is one complete wave, is your wavelength. And how many are there? So we've got, basically, that's going to be 1. Let me just copy and duplicate this. So that's going to be 1. Let me just draw them better. Yeah, 1. Also another one here. 2, 3, 4, 5, and 6. So we have 6 of our wavelength, basically. 6 times our wavelength. Basically, that's our distance. Basically, this is the distance from that to that. We're also going to do it to here. So from here to here, that's 1 wavelength. 2, 3. Why is it so disgusting? It's really struggling. Wow. All right. I don't know what's happening. So 1, 2, 3, 4, and that's the last one, which is 5. So this has 5 of the wavelength. And remember, the path difference is the difference between those two distances. So, let's write that down. So PD, which is your path difference, is basically 6 lambda minus 5 lambda, which is left with lambda. Basically, this is our path difference. And so it's basically your wavelength, which is that. So it's the same as that. So using your information, calculate the path difference between the two, arriving to give you a reason why. Beautiful. That is it. Path difference. You can't show in calculations. And so basically, it's just the same as 0.025 because it's the same as your wavelength. 1 of your wavelength. That is it. That looks good. Will the intensity of the microwaves at the detector position, as shown in figure 9, be a maximum or a minimum? Now, what it means by maximum means that is there constructive interference that happens there, or is there destructive interference, which means that it's a minimum? Now, that's easy to answer because we just calculated the path difference, which was lambda at this detector. Now, because we know that the path difference is an integer value of the wavelength, this means that constructive interference has happened, and so it has to be a maximum. We can see that your path difference is an integer value of the path of the wavelength. Remember, so if your path difference is an integer value of your wavelength, it means constructive interference happens, so it has to be a maximum. So let's write that down. All right, so it's only 2 marks, so let's write a nice one. So we're going to say it's going to be a maximum the path difference is an integer value of the wavelength. That is it. Done. D. The frequency of the microwave is now halved. So remember, if you halve your frequency, you double your wavelength, assuming that the speed is constant, of course. And it is, because it's the speed of light anyway. So what's going to happen to your wavelength? It's going to double. And the position of the detector is not changed. That's good. So the position is not changed. Describe any changes in the intensity of the microwaves at the detector and explain your answer. So at the detector, sorry. So basically our new wavelength is 2 times our original. That's what's happened. So I'm going to write that down. Your new wavelength, so lambda nu, n, is 2 times your original wavelength. So let's do the same thing. See if it's a maximum. So the intensity, is it a maximum or a minimum? So all do the same thing. So I'm going to basically rub these out now. All right. So because we know that your new wavelength is basically 2 times your original, so we're going to consider 2 of the waves to be 1. So basically that's going to be 1 because that's 2 of the waves. And that's 1. So that's another 1. And that is another one. So we have actually 3 lambda, 3 of the new wavelength. What about this one here, this part here? So that's 1, and that to that, that's 2, and then 2.5. So basically 2.5 of the wavelength. So you remember the path difference. So let's calculate the path difference basically. So PD is basically 3 minus 3 lambda minus 2.5 lambda, which gives us 0.5 lambda or wavelength. All right, so because now, look at this. Because the path difference is not anymore an integer value of the wavelength, this tells us that destructive interference happens, and guess what? It's a minimum now. Beautiful. What if this was a nice question actually? So basically, minimum as wavelength. All right, so wavelength. No, what am I saying is wavelength? As path difference. Sorry, I was going to say as path difference is 0.5 of the wavelength. So destructive interference happens. Beautiful. Next question. Question 14. Students are conducting an experiment to investigate how the path of a light ray from a laser changes when the light passes from one medium to another. They direct the light from air into the rectangular glass block and change the angle of the ray until it emerges back into the air parallel to the surface of the block. So what's happened is basically, from what I'm hearing, this is different. So you can see they've kind of perfectly angled it. So now that it's the wave, your ray is between the air and the rectangular, basically glass block interface. So basically it's here. So basically that's our critical angle. And change the ray until it emerges back into the air, parallel to the surface of the block as shown in figure 10. Describe how the speed of the light ray changes as it enters the glass block. Let's see. Now, let's see what's here. So let me use a different color. All right. Now, basically, you know, the laser was, let's say N1. Basically, N1 means air. Let's say N1 is air. It's the refractive index of air, which is 1. So as the light rays, laser goes to the rectangular glass block, which has a refractive index that's greater than the air, basically. So N2 must be greater than N1. So the refractive index of the block, of course, is greater than the air. If you're going from a low refractive index to a high refractive index, your speed decreases, basically. The speed of the ray decreases as it enters the block. So yeah, so basically I would just write, so speed decreases going from high, sorry, what am I doing? From low to high refractive index. Refractive index. Beautiful. Does that sound? So describe how the change of the light. I mean, you only need to say the speed decreases basically to get that mark. But yeah, going from low basically to high refractive index. B, the student measures the angle, this shown in figure 10, to be 41 degrees. So that's our critical angle. Use this information to determine if the glass is most likely to be crown glass, which has a refractive index of 1.52, normal flint glass, which is 1.59, and heavy flint glass, which is 1.66. Show you're working out. All right. So to do that is, okay, it's going from here to the basic critical angle. So we know that the critical angle formula is what? Oh yeah, by the way, you don't need to know this. This is not anymore in the study design, so you guys are lucky. Basically, N1 sine theta C, which is your critical angle, is equal to N2. So N1 is basically, we're going from the glass block, which is our glass block. N1 is our glass block. Sine, your critical angle was 41, we said. And N2 is what? N2 is going back to the air, which is 1. So basically, N1 is 1 over sine 41. Which gives me 1 over sine 41. So that gives me 1.5 1.52, which is what? So 1.52 is your crown glass, basically. Your type of glass is crown glass. Beautiful. Question 15. Let's have a try at this. Figure 11 shows an apparatus used to study the photoelectrical effect. Light of various frequencies and intensities can be shown into the metal plate inside an evacuated cell. This sometimes results in the release of electrons. The voltage of the power supply can be varied and the direction can be reversed. Beautiful. So the graph in figure 12 shows the variations of photocurrent with voltage for 3 experiments, A and B and C, using light of different frequencies and intensities. Beautiful. Now you should straight away realize intensity affects photocurrent. Frequency only affects your stopping voltage. First thing always. Don't forget about that. So we have this. So it says A, using the term half, no change or double, how would the intensity and the frequency of the light used in experiment B need to be changed so that the experiment B gives the same results as experiment A? Alright, so let's just make these nicely color coded so I can show this. So like that, let's make this red, basically this one here. So just kind of nice. Make this red. Basically this one purple. And this one blue, basically. Beautiful. So what we're doing is basically we're going from experiment B to experiment A. What should we do? So experiment B, which is the purple, to experiment A. So we can see that the photocurrent is the same, meaning that the intensity there's no change in intensity, basically. So we can say no change. Because if there was change in intensity, you would have seen the photocurrent basically different. And we can see that they're not different. They actually are the same. So, but what's the actual difference is that you can see that the stopping voltage of A is larger. Means that the frequency used has to be doubled. Does that look right? Yep, so doubled. So I want to read this. So that the experiment B, which is basically the purple, goes to A. Yep, so you can see the stopping voltage is higher, so the frequency had to be doubled. Beautiful. B, using the term half, no change, or doubled, how would the intensity and the frequency of light used in experiment B need to be changed so that experiment B gives the same results as experiment C? So we're going from B to C. So B to C, what can we see? Well, we can see that now the photocurrent has decreased. So it means your intensity had to be decreased, so halved. So, okay, so your intensity is halved. Halved. Frequency? So what about the frequency? What about the stopping voltage? So we're going again, so B to C. So B and C, we can see that they have the same stopping voltage, meaning that there was no change in frequency. No change. Beautiful, and that's it. Question C. Let's have a try at this question. The metal plate is made of metal that has a work function of 2.93 electrovolts. Determine if the photoelectrons will be ejected from the metal plate when it is illuminated by light with a wavelength of 700 nanometers. Show your working hour. So for photoelectrons to be, to be basically ejected, what we need is the energy of the photons to be greater than the work function. So let's calculate those energy of the photons. So energy of photons is hc over wavelength. So basically, if I want to, so that looks good. So h is basically, look at my summary sheet, 4.14 times 10 to the negative 15. Is that right? Yep. Times your speed of light. All being divided by your wavelength, which is 700 nanometers. That gives me what? So let's try to check that. So 4.14 times 10 to the 15. 0 times 10 to the power 8. 700 times 10 to the negative 9. So that basically gives me 1.77 electrovolts. Now we can see that the energy that's given is lower than the work function. The energy of the photon is lower than the work function. That tells us that no photoelectrons will be emitted. So as your energy of photons is less than the work function, so energy of the photons is less than the work function, no photoelectrons will be emitted. Beautiful. Next question. 16. Let's have a try at this. Figure 13 shows the diffraction pattern produced by an X-ray beam consisting of photons of energy of 400 electronvolts. Show that the wavelength of an X-ray photon is approximately 3 nanometers. Beautiful. So we know that energy of a photon is hc over wavelength. So wavelength basically is hc over energy, basically, of a photon, which is, so what's our h? Basically, it's again, so 4.14 times 10 to the negative 15. Your c value is 3.0 times 10 to the power 8, your speed of light, and divided by your energy, which is 400. So that gives me what? Alright. Negative 15. So, yep. So 4.0 times 10 negative 15 times 4.0 to the power 8, and then 400. So that gives me basically, because we're showing you that it's, okay, times 10 to, 1 times 10 to the power 9 to get nanometers. Basically, that gives me the wavelength to be 3.1 nanometers, which is approximately the same as 3 nanometers. Done. So we've basically shown that. Next question. B. A stream of electrons produces a diffraction pattern with the same spacing as X-ray diffraction pattern shown in figure 13. Calculate the speed of an electron in the stream. Take the mass of the electron to be that. Beautiful, easy question. So, basically what I'm going to do is, because I wanted the speed, I should just calculate the momentum. So, momentum is, having a look at my formula here, I just want to make sure no mistakes happen, is h over your wavelength. Now, we know our wavelength is basically 3.1 nanometers. So that's going to be, because remember the momentum is going to be the same for both electrons and the the X-ray basically. Yep, photons. Okay, so basically h is what? So h, we want the original h, so 6.63 times 10 to the negative 34. And we're going to be dividing that by your lambda, which is your 3.1 times 10 to the negative 9 meters, which is your thing. So you get that there. All right. All right, so we're going to basically times 10 to the negative 9. So we got that. And so 6.63 times 10 to the negative 34. Divided by the answer. So we get, basically in terms of momentum, we get basically 2.13 times 10 to the power of negative 25 kilograms meters per second. And now we can remember momentum is mass times velocity. So velocity is your momentum over your mass. So our momentum, the one that we calculated, is 2.13 times 10 to the negative 25 divided by the mass of an electron, which is 9.1 times 10 to the power of negative 31. Okay, that looks perfect. Let's put that in. So 9.1 times 10 to the negative 31. And so that gives me, to two significant figures, 2.3 times 10 to the power of, so 1, 2, 3, 4, 5 to the power of 5 meters per second. Beautiful. That looks right. Is that right? 1, 2, 3, 4, 5. Yep, that's good. Question 17. Describe how absorption line spectra are produced and describe their relationship to electron transitions within atom. Beautiful, easy question. Now, let's have I'm going to explain it by basically, like the absorption line spectra. I'm going to actually visually draw it to explain how it works, so you can make so much sense. What it is basically, it's like because you have a visible, it's the visible spectrum of light. So basically you have, your purple, which is your strongest. So I'm going to use my highlights. I'm going to use purple, which means your strongest basically frequency, because remember, as the strongest frequency, then it gets a little bit to darker blue, if I wasn't mistaken. So it's a little bit darker blue. It's like a darker blue, some lighter blue basically. It's a little bit lighter blue. Gets to like greener. Gets green. It gets yellower. So you remember it goes from purple, means the highest frequency, to the lowest frequency bit, which is red basically, which is to the right normally. Which is yellow here. You have yellow also. Oh, why did I do that? Yellow is there. Actually, orange would be the typical one around here. Then yellow, which I'm gonna basically just shade over here. Alright. So basically this is how it looks like a basic rainbow, but remember, this is what our absorption spectrum looks like. It's like it's a full spectrum of the visible light, and what happens is this is what happens. So basically the absorption spectrum shows the frequencies or the wavelengths of light that a particular atom or element will absorb when basically light is shown to it. So for example, say you have an atom and basically you shine light that has the continuous spectrum of light. What's going to happen is that the element is going to absorb some certain frequencies. So you'll have some dark bands here. So because it's going to be absorbing some frequencies, so there's going to be some black places here. So let me just use a different color. There's going to be some dark spots here, like a spot here, some lines or dark bands. Like that. This is nice. Yep. And so basically what this dark band tells us is that certain frequencies or wavelengths of light are basically absorbed by these elements. Not all the frequencies, certain. So that's the key here. And so what does that tell? Like, what do the dark bands actually tell? So it just tells us that remember that these frequencies over here, these frequencies tells us that what the element basically consumes or absorbs to transition to a higher energy level. Remember? Because if it absorbs energy, it's basically transition to a higher energy state when it's going to other states. Yeah. So I think that's what we just basically need to explain. I hope that makes sense, how it would look like. Yeah, so how much? 3 marks. All right, so I hope that, I think that's a nice explanation too. All right, I'm just going to basically write. You should normally have this kind of stuff in your formula sheet, like a nice detailed summary of it. So whenever you come into the exams, you can easily summarize it in the exam. So let's do that. I'm going to use basically light blue. All right. So we're going to say, what's big font? So here. And absorption basic spectra shows the frequencies. You're saying frequencies or wavelengths, basically. Frequencies or wavelengths of light that a particular element or atom will absorb, when the full spectrum, so when the full spectrum of light is basically shown through it. Yep, so shown through it. Beautiful. Now, that's a nice summary, and we're going to say absorption spectra consists of the continuous spectrum of light with dark bands, so with dark bands or lines, you can say lines, but dark bands is more, at the frequencies of light that a given element will absorb. Nice, absorb. And so basically, I'm kind of going into detail, but so the dark bands, so the dark band in the absorption, absorption spectrum consists corresponds to electrons, so basically, because we want to, basically what it means is when it absorbs, they go to a high energy state. So electrons, so corresponds to electrons in the element absorbing those wavelengths and transitioning to a higher energy level, That's it. I think that goes in very detail. Yeah, 3 marks. Wow. Question 18. Let's have a look at this one. Provide an example of an instance in which classical laws of physics cannot describe motion at very small scales and explain why they cannot. What a beautiful question. This is actually, there's one significant experiment that kind of explains this whole thing, and I think that's what they want. Provide an example of an instance. Yeah, so basically one of the instances that wasn't basically explained by classical physics is when an electron is basically hit through a single slit. And these basic single slits can be like a lattice, a crystal lattice, or anything. But for example, let's see here. I'm going to draw a nice diagram to kind of correspond to this. All right. Now, say you had an electron, basically. Big electron, kind of nice. And basically, it's going, we're shooting it through the slit at, high velocities. Now, by classical physics, we know that, say we had a scream, actually. Let's say we had a scream in here. And basically, in classical physics, what we would assume is that this electron basically goes in a straight line and hits the scream at a point. So there's be a dot. But when they did the experiment, they didn't see that. They saw a diffraction pattern. And they were like, what? Why is that? So remember, if basically what they saw was this. So they saw basically black, so they saw dark spots. So like dark and white spots. So dark, white. So sorry, that's what going to be like white, dark, white. And they saw this diffraction pattern. So they saw like a diffraction pattern and they're like, what? How can matter like electrons passing through a slit diffract? Because it's not a wave. That's what they assumed back in those days. And so now they've basically, from this experiment, what they learned is that classical physics cannot explain it, of course. And so they overall learned that, that matter, such as, electrons, basically behave as waves at very small scales. And so this is what kind of explained it. And the whole kind of theory about this is called the wave-particle duality, where waves and particles basically have this dual nature. They can actually they can basically have the same, can work together at very, very small scales. And basically that's why classical physics, I think this is one of the most easiest kind of thing to talk about, an instance. So basically like an electron going through a small, gap, and basically it diffracts, which is basically a wave property. Diffraction is a wave property, and so why does it do that? And yeah, I think we'll explain that, and that's what they pretty much mean. What a beautiful example of a question to use. All right. So we're going to use color orange. It's right in our statement. So, like we said, so we're just going to explain the experiment. So, oops, that's too large. So when electrons travel through a small gap like the space between atoms, basically like crystals, so between atoms in a crystal, they are supposed to go in a straight line. But this is not what happened. Is this not what happened? They diffract. Forming an interference pattern. Since diffraction is a property of waves, this shows that matter can behave like waves at very small scales, This is called wave-particle duality. Beautiful. I mean, that goes too much in detail, but I think it does answer the question. Yeah, I hope that makes sense. And yep. Question 19. Figure 14 shows the energy levels of sodium atom. Alright, so a sodium atom is initially in the n equals 4 state. Excited state. So basically it's initially here. Why is it? Come on, draw me a straight line. There we go. Calculate the highest frequency of light that a sodium atom in this excited state could emit. Now remember, the highest frequency means the highest energy. And so the highest energy, of course, is basically going to 0 because that's the longest arrow you can basically build from all of those energy states. Yeah, so which is basically 3.61 electrovolts, basically. 3.61 electrovolt. And so we just want to calculate the frequency of it. Now, we know that, just looking at my formula sheet, if we have the energy of a photon, okay, so we know that energy of a photon is h times your frequency. And so we want to calculate this frequency. So frequency is your energy over your h. So wait, what am I doing? So so we're trying to calculate, so we have frequency. Okay, perfect, makes sense. All right, so what's our energy? It was 3.61, all being done by h, which is 4.14 times 10 to the negative 15. Let's check that. 3.61, 4.14 times 10 to the negative 15. So that gives me basically the three significant figures, 8.72 times 10 to the power of 14 hertz. Beautiful. That looks good. Yep. B, let's have a try at B. Figure 14 shows some specific energy levels that electrons in a sodium atom can occupy. Describe how the wave nature of electrons explain the existence of the energy level shown in figure 14. What a beautiful question. You should have, if I'm going to tell you right now, in every past paper that I see, this question is so many times repeated that it's so easy to get full marks. Now, but when you just hear this question, it's basically just talking about, like, you just need to say, like, how basically electron standing waves are basically formed, and so how it basically describes how they are quantized energy states. So make sure you have what I'm going to write here. Make sure you have it like a nice kind of summary in your summary sheet, because whenever you get this question, you can easily summarize it and put it in your exam when time comes. So basically, for this question, just read it, because you want to answer the question first. Describe how the wave nature of electrons explains the existence of the energy level shown in figure 14. Okay, so we can give a lot of dot points. So first we can say that electrons demonstrate wave properties because they have a de Broglie wavelength. Because remember, having a wavelength means that, they have wave, basically like wave duality between them. So it can act as a wave. But the main important thing is that you need to explain that electrons only orbit when it's basically orbital circumference is in the correct length. So not all lengths works. So there's only certain lengths for basically an electron to exist as a standing wave. And so so you have to think about it. If there are certain correct lengths, this tells us that there are certain electron energy levels that electrons can basically create a standing wave, meaning that electron energy levels are quantized or discrete, or have only certain levels they can become standing waves. And so I think that's all you need to basically say. So we're going to read, and I think just an extra one thing that I always like to do in exams is basically just say write the formula, because we know that electrons can only form standing waves when their orbital circumference is a whole number of the de Broglie wavelength. So we're going to basically write that too. It's very useful sometimes in exams, just basically writing it, because it's very detailed, I would say. All right. So let's say electrons demonstrate wave properties and have a de Broglie wavelength. So electrons only orbit atoms when the orbital circumference, circumference is the correct length. So it's the correct length for electron to exist as a standing wave. Therefore, electron energy levels are quantized or discrete. And I think just a little extra thing that you can say is since electrons, basically write that formula, the standing waves, for a standing wave to form, the orbital circumference is has to be a whole number multiple of the electron's de Broglie wavelength. So since electrons can only form standing waves when orbital circumference is a whole number multiple of de Broglie wavelength. Beautiful. And so this is the formula. So it's n lambda equals 2 pi r. So the circumference of a circle. Beautiful. All right. Question 20. Is this the last question? Yes, it is. So it's the graphing one, analysis question. Let's have it finish this exam. A group of physics students used a double-slit interference experiment to measure the wavelength of a light from a laser. The laser was directed at right angles towards a double slit in a darkened room, and an interference pattern was observed on the screen. The arrangement is shown in schematically here. All right. The student had access to 2 double slit slides, one with a slit spacing of this and the other slit spacing of this. They basically placed the screen at a distance of L equals that, and that. So they can change L, and they can also change the slit spacing and measure the average distance. So what they're measuring is average distance change in x from the central bright band to the first bright band. Identify the dependent variable, the independent, and the control variable in this experiment. Beautiful. So remember, let's do the independent variable. So independent variable is the variable that you can manipulate or you can change. For example, I'm just going to choose one because there's two. There's slit spacing and there's the distance between the screen and the slits. So I'm going to say slit spacing. Your dependent variable is the thing that you're measuring, which is basically your average distance. Which is your change in x. Your control variable, your control variable is the variable that you don't change. You keep it constant. It stays constant throughout the experiment. And one thing is, because using the frequency of laser is constant, like the same frequency. So frequency of light, basically. Frequency of laser. Yep, frequency of laser, basically. Keep that constant, basically. You can let that be constant. And yeah, beautiful. The experimental measurements taken are shown in table 1. So we're given the length, D, and we want to, L over D, no units, times 1,000. Change in x is that. The students used the approximate equation this and a graph of change in x plotted against L over D to find a value for the wavelength. Calculate the values of L over D to 2 significant figures and write them in this table. All right, let's do that. So, so we're doing length divided by distance and no units. One thing you can do or not is they don't change this to meters, because they're both millimeters, and what you do is they're both distances, and so when you divide both distances, they're going to actually cancel out. It's going to be the it's a waste of time basically making them meters, because it will still give you the same value. So what's that divided by that? So what's 1,500 divided by 0.26? It gives me 5,769, but it's been times already by 1,000, so we want to make sure divided by 1,000. So that's going to give me two significant figures, 5.8. Be careful, because remember 5.8 times 1,000 is going to give me that value. Yep. So let's do the other part. So 2,500, 0.26 divided by 1,000. That gives me 9.6. Next one, 2,500, 0.26 divided by 1,000. 13, 1,500, 0.16 divided by 1,000. That gives me 9.4. 2,500 divided by 0.6 divided by 1,000. That gives me basically 16. And 3,500, 0.16 divided by 1,000. That gives me basically 22. Done. Plot the values from table 1 on the grid below. Include an appropriate scale, numbers and units on the y-axis. Include an appropriate scale and numbers on the x-axis. Include uncertainty bars in the y direction of 0.5 millimeters. No uncertainty bars are required in the x direction. Draw a linear trend line throughout the plotted points. Beautiful. So first, we have L over D, and we got it here. So it's no units, and we're also going to make it times 1,000. So it's going to be no units. Make sure it's times 1,000. So we're going to basically use these values over here, and already, change in x is going to be in millimeters. We're going to keep it in millimeters. So basically that, as millimeters. That is it. And we're going to approach scale. So let's do that. So L over D is what? It goes to 22 is the max. So if I basically went one by one for each, so like that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Good, it actually works. So each square, small square is 1, has a 1. So what I'm going to do is nicely, it's going to be, that's 1. 2, sorry, what am I doing? Oh my god. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. What about change in x? So the change in x, the max is 12. So I think, because there's little squares, I think going, basically each 2 squares is 1. So like, that means that 4 blocks has to be 2. So like, that's going to be 1. Does that work? So because, let's say that's 2, it's 4, 6, 8, yep, 10, 12, yeah, that works, 14, beautiful, that works, done. And so now let's plot those points. So I'm going to use a color of, use green to, so let's plot the first point. So 5.8, so 5.8 is where? So 5's here, so 5.8, so that's 5.5, so around here basically, like that. And so 5.8, and the change in x is 3.3, which is, that's 3, that's 3.5, midway is around here basically. I'm just going to draw it like that. I'm going to rub those parts out. Done. So that point is there. Next point, 9.6. So let's have a draw at 9.6. So 9's here, 9.5, 9.6 around here. There we go. So 9.6 is there. 5.5. So basically that's 5. 5.5 is here. So basically it's on the line. Let's rub those out. Done. Next one. 13. So 13 is basically here. So 13, 7.7. So 7's here. 7.5. 7.25 around there basically. Midway through that. So I'm gonna rub that out. 9.4. So 9.4, so that's 9. 9. Around here basically. Here, and so 4.9. So 4. That's 4.9. So 4.9 is around here. Around there. Done. Alright, so 16. Basically that. So 16, 8.2. 8.2, so that's 9, 9.5, 8.2 is around here. That. 16, 8.2, yep. So that's because 8.5, 8. Yep, that was good. 22. So 22 is basically here. So 22, 12.3. So 12 here. That's 13. So 12.3 is around here. Basically, so around here. So I'm going to rub these out now. And yeah, that's what it looks like. I just want to make sure they look so disgusting. I mean, they don't look nice. I want to make sure they are proper. So, because they don't, yeah. Because they're saying passes for a straight line. So I can see that the first, they look, yeah, I mean, hopefully they do pass through all of them. So I'm going to now draw the, so I've drawn the units, drawn the axes, include uncertainty bars. Let's include this uncertainty bars, 0.05 in the y direction. So basically, if that's 1, I mean 0.5, it's like that basically. It's 1 box each. So basically I'm going to copy this. I'm going to use this as a estimate basically. I'm going to copy this part here. I'm going to duplicate it right there, put it there. There we go. Duplicate it again, put it right there. Duplicate it, put it right in the middle. Duplicate it right there. Duplicate it right there. Last and lucky all. Right there. And so I'm going to draw a straight line. Yellow straight line. That passes basically through all of them. Yeah, it does pass through them. It actually does nicely passes through all of them like that. Yep, that looks quite good. I mean, it does pass through them, so that looks good. Yeah, I've drawn, that looks like that's it. Perfect. Calculate the gradient of the trend line. Show all your steps are working out. Beautiful. So gradient is just m. We just need 2 points on the graph, basically. So 2 points that are nice. The 2 points that I would take are the ones on the line. So this point looks good. So I mean, it doesn't. You can't see it, but I'm going to show it here. So here, that point here with the red. Actually, let me get another color, orange. So basically, this point here looks good. So that to that. Another point that lies on the graph looks like basically this point here, which is here to here, and that is it. So I'm gonna make sure, okay, because it's in millimeters, so the y is in millimeters, so it's gonna be 11. So I'm gonna here, it's gonna say 11 minus basically 5. Make sure to change it to meters. Times 10 to the negative 3. Yep, because it's in millimeters. Yep, to make it meters. And then the x values are 20 minus your 9. And that's you multiply by 1,000. And that's going to give me in meters. So that's going to give me 11 minus 5. Something like 3, 20 minus 9 times 1,000. So that gives me, what the hell happened here? Alright, so times 10 to the power of negative 3. So it gives me this. Oh, we want in millimeters. So that's a meter. So just basically times it by 1,000 to get in millimeters. I get approximately 5.5 times 10 to the power of, so 1, 2, 3, 4, negative 4 basically. Millimeters, beautiful. That is it. So E, use the gradient from part D to determine the wavelength of the laser light, give all your steps, show your working out. Alright, so what I'm going to do is, we know our gradient is our rise over run. So gradient M is, what were we doing? What is our Y values basically? It was our change in X, all being divided by L over D. So L over D, which is basically change in X, D over L. That here is our gradient. So I know that change in X, remember the formula, change in X is equal to length times your, lambda times your length over D. Wait. I think I see something. Wait. So change in X here is our Y values. So we can write it as Y lambda L over D. So L over D here is our X values. So we can write it as X. That means the gradient of the line is our so the gradient of this line is our wavelength. Because remember, y equals mx. Y equals mx. So x is our here, and our m is our so m means our gradient. So it is our wavelength. So the wavelength of this line is basically our. So the gradient of this line is our basically wavelength. Beautiful. So let's do that. Determine the wavelength. It's basically, yeah, it's the same thing, but it's in meters now. Oh, so it's divided by 1,000 now again. So that's the same value, but divided by 1,000. Okay. So basically it's 5.5 times 10 to the power of 1, 2, 3, 4, 5, 6, 7. So negative 7. Is that true? 1, 2, 3, 4, 5, 6, 7. Yep, negative 7. And because it's 2 marks, we just want to explain. Basically, gradient of line is wavelength. Gradient of line is wavelength. As basically change in X equals lambda L over D. It's basically just the same as Y equals mx. Basically, that's it. Done. That's the whole paper. I hope you guys enjoyed this video. Please make sure to like and subscribe and share this video with your friends. And make sure you guys take care of yourselves. I hope you have a great day and bye-bye, bros.